Good evening to one and all. Is the audio clear? And the video also? Tell me. Thank you. So, in the previous class, we discussed about the definition of Euclidean ring. So in today's session, we will take the concept of Euclidean ring one more time and let us do some results based on the Euclidean ring concept. So if we look into the definition, initially we consider an integral domain. This integral domain having an additional property. That property is nothing but we are able to define a function d satisfying two conditions. If such type of function d is existed, then we say that this integral domain will be called as an Euclidean ring or Euclidean domain. Coming to the conditions of the function, it is the first condition is always d of a is less than or equal to d of ab whenever you take two non-zero values. And second condition is you are able to write a equal to bq plus r, where q and r also belong to the same set, where the remainder r is 0 or d of r is less than d of b. These are the two conditions. Right? So if there exists a function satisfying these two conditions, then we say that it is an Euclidean ring or Euclidean domain. Is it clear? The definition part. Please take a note of this. Now, the first result what we discuss is the ring of integers z plus dot is an Euclidean ring. The ring of integers z plus dot is an Euclidean ring. That was the first result. So how you are going to prove it? We know that it is an integral domain. We already know this. So we are going to define a function from z minus singleton 0 to z by d of a is equal to modulus of a. Now you can observe that how we have defined, excluding the 0, for the remaining elements you are defining a function from the integral domain to the set of integers z. Always the function is giving an integer value to us, and the integer value is either 0 or positive. The result should not be negative, right? And how I am defining the function? I am defining d of a is equal to modulus of a, because the result should be either positive or 0 integer. It should not be a negative integer, right? Now I am going to prove that the function d, what I have defined, satisfies the two conditions of Euclidean domain. Okay? You please take a note of this function. Is it noted? Right. So, coming for the first condition of it, we can say that always d of a is greater than or equal to 0. You agree or not? Yes. Now, if you take two values, a not equal to 0 and b not equal to 0, now you consider d of ab. As per the function definition, it is modulus of AB, and always we can say that this is greater than or equal to modulus of A, nothing but D of A. Because as we know that modulus of AB is nothing but modulus of A into modulus of B. So it will be greater than or equal to modulus of A. Therefore, the first condition is satisfied. Accepted all? The first condition. Coming for the second condition, you take two elements and the second one is a non-zero value. So whenever we take two integers, by default the division algorithm holds. In integers, you have the division algorithm. Whenever you have taken two numbers, you can write one number as divisor into quotient plus remainder. It is common. So you can write a is equal to bq plus r, where q comma r are nothing but integers. Either r is 0 or r is less than b. So here a is the dividend, b is divisor, q is quotient and r is remainder. Since you are dividing a with b, so the remainder has possibility that either remainder is equal to 0 or remainder is less than b. Accepted? Now what happens from this very condition? As we know, r is less than b implies modulus of r is less than modulus of b. This implies d of r is less than d of b. Therefore, second condition is also satisfied, because whenever you take two values, you return in the respective form and satisfying the mapping condition. Therefore, z plus dot is an Euclidean ring in which the function is defined as d of a is equal to mod a. The underlying idea here is, whenever you have an integral domain, you should be able to define a function in any manner. The function need not be unique. You can define the mod a or in any other form, such that the function must satisfy the two properties. If it satisfies the two properties, then we say that it is an Euclidean ring. If you are unable to define at least one function satisfying the two conditions, then it is not an Euclidean ring or Euclidean domain. Okay? Clear for all? So if we have noted this, then I will take the next concept. I mean the next result. Right. Another thing is, Every field is an Euclidean ring. You please take a note of this question. Every field is an Euclidean ring. So for the solution part, you consider a field F plus dot. Now what happens? You are going to define a function from non-zero elements of F to Z. So you are removing the zero element from F. So let us give the name as it is F star. So D is a function from F star to Z. And how I am going to define it? I am just defining it as the constant function. So you define D of A is equal to 0. Simply the value is nothing but 0. So I am pairing all the elements with a single 0. So you can imagine that if this is F star and this is Z, so all these elements are mapped with 0 only. Are you clear now how the function is defined? Say. So by default, whatever the value you take, D of A is always greater than or equal to 0. Now if you take two elements, A and B not equal to 0 in F star, so if you consider D of AB, the value is nothing but 0. And also if you consider D of A, the value is also 0 because you have taken the constant mapping. So the condition D of A less than or equal to D of AB holds. So in this way, the first condition will be satisfied under this mapping. Any questions for anybody? Tell me. Right. Now, coming for the second condition, you take the values A comma B belongs to F or F star. Now, I should bring the form of division algorithm here. So if you consider A, you can write it as A is equal to A dot 1 because 1 is the multiplicative identity, the unity element. So this can be written as A dot B inverse B because in the second condition always we take B as a non-zero element. Since F is a field, the special property of field is if you take any non-zero element, it always possesses the inverse. So if you take the element B, its inverse is nothing but B inverse. If you multiply them, B dot B inverse is nothing but 1. So you can write 1 as B inverse B. So if you apply associative law, you can write it as AB inverse dot B. So the value A is written in the form as B into AB inverse plus 0. So it is of the form A is equal to BQ plus R, where remainder is 0 and the quotient value is AB inverse. Therefore, second condition is satisfied because the possibility of R must be either 0 or D of R less than D of B. Here I have taken that the remainder is nothing but 0 itself. Therefore, the second condition is also satisfied. Hence, it is an Euclidean ring. Okay? Any queries for anybody? Please tell. If you have noted, I will take the other one. So here, if you observe that you have defined the value as 0, you can change the mapping also. You can define it as d of a is equal to 1, the number 1. So in this way also you can prove that it is an Euclidean ring. So the main thing here is you should be able to define a function which is satisfying the two conditions. Please understand, either r is equal to 0 or d of r less than d of b. This is the criteria. It is not mandatory to show that always d of r less than d of b. We should be able to say that this thing will happen if the remainder is not equal to 0. That's it. That is the only thing we need to show. Clear? In general, remainder will be 0. If the remainder is not equal to 0, in such cases, d of r should be less than d of b. That is the underlined idea there. Thank you. Any other questions, please? Anybody? So one more interesting property is, however, every Euclidean ring is a principal ideal ring. Every Euclidean ring is a principal ideal ring. Right? So here, I don't want to discuss about this proof because it is not that much important with regard to exam point of view, but I will give the outline of it because the proof of this result is very similar to what we have done, that Z plus dot is a PID. So here you have considered that if you take an ideal U, then it may be a zero ideal or non-zero ideal. If it is 0, it is principal. If it is not a zero ideal, then you take the part that UV is bifurcated as the positive values and negative values, in which we take that B is the smallest element and UV is generated by this smallest element B. So this proof you have done already under the result that Z plus dot is a PID. Can you imagine that? The proof we have done earlier, the ring of integers is a principal ideal domain. Every ideal is a principal ideal. You have done that already earlier. Can you recollect that? Take a minute of time. All of you. So here, the same proof we rewrite here. We exactly reproduce the same steps here. Nothing changed at all. Since it is an Euclidean ring, it has a function D satisfying the two properties. So we reproduce the same steps as it is without changing anything, except writing U plus. So if you take an ideal U, if it is 0, it is principal, okay. If it is not a zero ideal, then it contains the smallest element B, because if you take an Euclidean ring E, So if you take an ideal U, since D is a function here, all the images of U will be here. So since these are integers, you will get a smallest integer here. So you will get a corresponding number, say this is B. So UV is generated by B. The same steps we rewrite here. There is no need to do the proof separately, right? So as per the examination point of view, the proof is not important, but you can note this statement. Every Euclidean ring is a principal ideal ring. While proving the other results, it will be useful. Okay? We rewrite the same proof what we have done here. Similar steps, no change at all. The same steps we rewrite here. Clear? Yes or no? If you want me to write the proof here, I will write the proof here. You can take a note of this. Can I? Right? Then I will write the proof. You just take a note of this. Then you can simply understand that. Okay. Just take a note of the proof. I will just write it on board. You just read the statements what I have written, then you can recollect the procedure. You can compare the proof of the previous result that Z plus dot is a principal ideal ring. You can compare both proofs. Okay? Just take a note of this, then you can ask if you have any doubts on this statement what I have written. After noting, please inform. Does it making sense for you what I have written? Say. Anybody has any questions for the statement I have written on board? Right. Can I continue for the remaining proof? Right. What was on the last line? In the previous thing you are asking? Before erasing the board. Say. So here our claim is, you are going to prove that UV is generated by B. This is the last line. So our intention is, whatever the ideal you consider in the Euclidean ring, it is principal. So you have to show that there must be a generator for the ideal. So here I have considered X as an element in U. X is any element in U. So if you are able to write that X is a multiple of B, so it means that B generates the whole set U. Therefore, it will become the principal ideal. So directly the division algorithm property of the function, you can have the elements such that X is equal to BQ plus R, where the remainder is 0, or D of R less than D of B. Here what I am saying, here the remainder is 0 is compulsory, because D of R less than D of B property we cannot use. Directly the remainder becomes 0. So whenever the remainder is 0, it is nothing but X is equal to BQ. So X is written as a multiple of B. So U is generated by the smallest element B. Hence the integral domain D becomes principal ideal ring, the Euclidean ring. Now the question is, why R equal to 0 is compulsory? Now what happens if R is not equal to 0? So from this very equation, you have R is equal to X minus BQ. So this is the elements you have taken. D is the ring, U is the ideal. You have taken Q as an element in the ring. X and B are elements in U. Since UV is ideal, using ideal condition, BQ belongs to U. You have two elements in U, X and BQ. The difference also belong to U, because UV is ideal as per the first condition of the ideal. So what happens? R is nothing but X minus BQ. So you are saying that R belongs to U. And what is the one more property you have? D of R is less than D of B. So this is a contradiction. Why it is a contradiction? Earlier you have taken that B is the element in U which has the smallest image. Now what you are getting? R is having smallest image when compared to B. This is a contradiction to our earlier supposition. Therefore, R not equal to 0 is not possible. So the only possibility is R equal to 0, which is compulsory. Hence, it becomes the principal ideal ring. Same steps, same lines you have written for that proof also. Z plus dot is a principal ideal ring. You can compare the both proofs. No change at all. You simply rewritten the proof again. You can check on that. If you have the material available right now, you can compare both the things. After giving the definition of principal ideal, we discussed that Z plus dot is a principal ideal ring. You can check for that. So please take a note of this. If you have any queries, you can ask. I will wait. That's why I have said that you simply rewrite the proof of the result. You didn't change a single line. Am I correct? Except at the end, D of R less than D of B. There we mentioned that R is less than B. The only change is one symbol. The same proof you have written without doing any difference. So if you have noted this, then I will take the next part. Please let me know after doing. So can I erase this? Right. The only change between the two proofs is, in that result we mentioned that b is the smallest integer in u. Here we mentioned that b is the value which is having smallest image. That is the only single sentence which will vary between the two proofs. Rest of the thing is, each and every statement is very similar. No change at all in the whole proof. So, now coming to the interesting question that Z of I is an Euclidean ring. It is an interesting question. It is also asked in the previous year papers. If you understand this proof in a clear manner, the subsequent results are also very easy for you to understand. If you fail to understand this result, the upcoming result will be somewhat difficult for you, right? And what is this Z of I? It is nothing but set of all Gaussian integers. We call it as the set of Gaussian integers defined by Z of I or J of I. There are two notations for it. Set of all a plus ib such that a comma b are integers and I square equal to -1. So here you are going to prove that the set of Gaussian integers is an Euclidean ring. So the fundamental thing is, we know that Z of I is an integral domain, because whenever you consider the concept of Euclidean ring, you must first know that the set what you have taken is an integral domain. After taking an integral domain, you need to define a function satisfying the two conditions, then only it will become the Euclidean ring. Since we know that Z of I is an integral domain, we have proved this problem already. All remained with us is, you have to define a function d on this set satisfying the two conditions. Then it will become the Euclidean ring, right? So you please take a note of this, then we discuss with the approach. After noting, you please tell. Now, how we are going to define the function on it? So whenever you take a value, you define the function from Z of I minus 0 to Z by d of x plus iy is equal to x square plus y square. You define the value like this. Now see, whenever you take a value in Z of I, the coefficients are nothing but obviously integers. A is an integer, B is an integer. If you take the value x plus iy, x is an integer, y is an integer. So if you consider x square plus y square, it is also an integer. And since you are taking the squares, always it is positive. So d of x plus iy is always positive integer. Do you agree? And I will say that the value of it is always greater than or equal to 1. Because whenever you consider the integer, since you are taking a non-zero value, either x or y must be non-zero. So the smallest value you can choose is 1 plus I0, minus 1 plus I0, 0 plus I, 0 minus I. These are the smallest values here. If you take any big number in place of x and y, except 1, it will be somewhat different. So you can take 2 plus I, 2 minus I, minus 3 plus I, etc., etc. These are different. These are the smallest values. So whenever you apply the definition x square plus y square, For this, the value is 1, the value is 1, the value is 1, the value is 1. For the remainings, always the value is greater than 1. Accepted? If you apply the definition x square plus y square, whenever you take the value d of x plus iy, please check on that. If you take, let me say, you have taken that 1 plus 2i. If you have considered d of 1 plus 2i, as per the definition it is 1 square plus 2 square, the value is nothing but 5, it is always greater than 1. Accepted? So, if you take one value as 0, another value as 1, you are getting 1, 1, 1, 1, 1, the output value. If you take the smallest one, let me say you have taken 1 plus I. So, if you consider d of x plus iy, it is nothing but 2. So, the minimum possibility for the output is 1, or it will be greater than 1. You will not get a negative value, and you will not get 0 also. Accepted? Unless the input is 0, output will not be 0. So, you can say that always d of a is greater than 0. This condition is satisfied. Accepted all? Now let us take two values and we will do the remaining part. Now let us take two values that you take u is equal to a plus ib, v is equal to c plus id, belongs to z of I, both are non-zero. You take both values as non-zero. Now you consider the product. So if you consider d of uv, the product, d of, you are multiplying these two, it will be ac minus bd plus I into AD plus BC. And how it is defined? Whenever you have the A plus IB form, you should take the D value as sum of the square of the coefficients. So it is AC minus BD whole square plus AD plus BC whole square. Now you expand this value using A minus B whole square formula, and you expand this value using A plus B whole square formula. Then you can observe that the result is going to come as you can check on that. You accepted all? And you can write it as now what happens? It is always greater than or equal to a square plus b square. Because for every value, the value is greater than or equal to 1. So, this is nothing but d of u, because it is nothing but d of a plus ib. So, this is nothing but d of u. So, you can observe that the condition d of u less than or equal to d of uv satisfied. Yes or no? So please take a note of this. Any questions or in doubts for anybody? After noting, please inform. Any doubts to anyone? Now, you can observe an interesting phenomena that whenever you take two values, a plus ib, c plus id, if you are considering the product here, it is coming like this. Sum of the squares of the first term into sum of the squares of the second term coefficients. Did you observe it? Say. So you can say one thing, that if you have a property that what is the value of d of 2 plus 3i into 4 plus 5i. If I have asked it like this, it is nothing but 2 square plus 3 square into 4 square plus 5 square. That you can imagine from this very understanding. You agree all? Because in the second step of the problem, you are going to make use of this. Yes, it is just like the homomorphism that you can say. It is just like the homomorphism. Okay. Now, for the concept of Euclidean ring, two conditions must be satisfied by the function d. So here you have proved one condition. The second condition you are going to prove now. Right? Let us prove for it. So again I take the same values. So I take uv is equal to a plus ib, v is equal to c plus id, where v is not equal to 0, belongs to z of I. So our intention here is, you are going to write uv is equal to v into something plus r. This is also the remainder, say. We can call it as the quotient and this remainder. Either remainder equal to 0 or d of r is less than d of b. That we need to bring out as a relation. So this is the value u and this is the value v. Are you clear about the second condition, what I am going to prove? In other words, you can say you are going to write it as a plus ib is equal to c plus id into something plus something. This is quotient and this is remainder. So it is interesting. So in order to get this type of relation on this set, you need to do a small construction. So you just observe this very carefully. So first of all, I want to consider this value. This thing you consider. So you can rationalize this value. You can rationalize this value. So I am doing rationalization. You will have the part as accepted all. Please check. I simply multiplied the values and separated the terms. So it is of the form P plus IQ, where P comma Q are rationals. So this total value I am taking as P. This total value I am taking it as Q. So it is of the form P plus IQ. Since they are in the fraction model, numerator by denominator, so there are nothing but the rational values, because I have represented them in the form of numerator by denominator. Accepted all? Say. Now here the construction comes as, whenever you take the rational number, you can represent it as the integer part plus fractional part. I'll give a small example. Suppose we have taken the value 3.6. Are you able to write it as 3 plus 0.6 or not? This part we call it as integer part, and this part we call it as the rational part. All of you agree? So this construction I am doing by means of integers. Now I will write some calculation part. You simply observe and you can verify it by means of taking the numbers. Okay? So sorry. So you can write P is equal to integer part of P plus alpha, and Q is equal to integer part of Q plus beta, right? And we define, you can say that the values of these things are less than 1 whenever you write the fractional parts. Now we take this thing we consider. You just take a note of that. Just take a note of these values. This is the construction I have made. You can verify it by means of examples. Okay? After noting, you please inform. Right? So far, if you consider the thing, we simply did the thing as, you have considered A plus IB by C plus ID, nothing but U by V you have considered. The value of U by V is equal to P plus IQ. That you have taken. So our whole intention here is You got the result as u by v is equal to p plus iq. This implies u is equal to v into p plus iq. So here my intention is I am representing p and q using the integers. For that I have done this type of construction here. Now for our convenience, let us take some examples and verify whether this condition holds or not. So let me take, we can do with one thing, say suppose p is equal to 3.2. So this part is 0.2 alpha value accepted, the fractional part. So whenever you consider the fraction part, the starting value for the fractional part is 0. Up to 1, it cannot be equal to 1. Because let me say, if you take p is equal to 3, then the fractional part is 0. So the maximum thing you can take it as p is equal to 3.99. So it will not be equal to 1, right? So the fractional part will be either 0, it should be less than or equal to half, and it will be more than half and less than 1. These are the possibilities for it. Accepted? Everyone? So if you consider this example, since the fractional part is less than or equal to half, I will take m is equal to the integer part of 3. So this is 3. Right? And how I have taken gamma is equal to p minus m. Therefore, gamma is equal to 3.2 minus 3, 0.2. And I have mentioned that p is equal to m plus gamma. 3.2 is equal to 3 plus 0.2. Accepted? Please check. If anybody has any questions, you can ask. Are you clear about this? Please tell. Suppose we have taken another example that say, I have taken p is equal to 3.8. Here the fractional part is 0.8, which is greater than half. So as per the fractional part condition, I should take m as integer part plus 1. Therefore, m is equal to 4 because 3 plus 1 I need to take 4. And what is gamma? Gamma is equal to p minus m, nothing but 3.8 minus 4. This is nothing but minus 0.2. Therefore, p is equal to m plus gamma will hold. Accepted? So in this way I have bifurcated. So either you consider P or Q, whatever the case may be, using the criteria of integer part and fractional part, I am representing P as m plus gamma and Q as n plus delta. This is my whole thing. Is it clear for all? Let me know. So if you are clear, I will erase this part and go to the back side, the solution part of the previous case. Can I continue then? Right. So u is equal to v into p plus iq we got already. You have a value for p, you have a value for q. Let us substitute them. Therefore, u is equal to v into P means m plus gamma plus I into Q means n plus delta. I have substituted P value and Q value here. Sorry. So this is equal to V into m plus In plus gamma plus I delta. This is equal to V into m plus In plus V into gamma plus I delta. So this is, I am writing it as UV is equal to V into Q plus R. So therefore, or you can say this is the quotient. This is the remainder. So what is the quotient here? M plus In is the quotient, and this value belongs to Z of I. How can I say that this value belongs to Z of I? Is because the possibility for M is integer part or integer part plus 1. These are integers. So M is an integer. And for N also it is nothing but integer part of Q or integer part of Q plus 1. These are integers. So this is integer, hence this value belongs to Z of I. So quotient belongs to Z of I. Clear? Any questions for anybody? Please ask. Any questions for anybody? Are you clear? Right. And whenever you write divisor into quotient plus remainder form, not only quotient, remainder also belong to the set. So from this, U minus V into quotient is equal to remainder. So this value belong to Z of I, this value belong to Z of I. So difference also belong to Z of I. So this value belong to Z of I because Z of I is a ring. This is a value in the ring. This is a value in the ring. This is a value in the ring. Whenever you are performing addition and subtraction and multiplication over the elements in the ring, the results also belong to the ring. Therefore, this remainder part by default belong to Z of I. Okay? There is no doubt that remainder will belong to Z of I or not. It by default applies. Clear? If anybody has any questions, you can ask. Because V is an element, sorry, V is an element in Z of I, M plus In is an element in Z of I. Therefore, if you multiply them, the product is also an element in Z of I, isn't it? That's why. So U minus V into something belong to Z of I because it is a ring. At 0.8 is Q of I. You have to understand that it is transformed. You have totally removed that. Because there 3.8 is written as 4 minus 0.2, not 3 plus 0.8. Please understand. Because the point here is alpha and delta are nothing but the fractional parts. If you write gamma and delta, they will become the integer parts. Because if you write Z of I, let me say, if you are applying division algorithm, you are going to write x is equal to y into something plus something. This must be an element in Z of I, and this is also an element in Z of I. So if the coefficients in this part are not integers, it cannot belong to Z of I, isn't it? So if you write gamma and delta, like P is equal to m plus gamma, Q is equal to n plus delta, so gamma and delta are nothing but the integers there. That is the underlined idea there. Okay? That was the underlined idea. Are you clear now? Say. Fine. Now, you have represented the form u is equal to v into quotient plus remainder. Please understand, you have taken the fractions actually. For your computational convenience, I have written like that. Just understand one thing, that actually you are taking p and q values as rational values. So you are going to represent them not in the form of decimals, in the form of p by q, the rationals form. So if you take p is equal to 4 by 5 and q is equal to, let me say, some 7 by 8 or something, or 8 by 9 or 8 by 5. So are you able to represent this p as in the form of rational and something? Suppose if you take q, q can be written as 8 by 5 is nothing but 1 plus something. It is also in the form of a fraction, isn't it? And you are converting that in terms of integer. So if I take a fraction and do that bifurcation, you will get confused. So for your understanding, I have written by simply taking a decimal like 3.2, 3.8, etc. So it will be easily understood for you. So actually, if you have bifurcated 8 by 5, what is the fractional part here? 3 by 5, isn't it? Am I right or not? So this 3 by 5 is greater than or equal to half or less than or equal to half. What is the part here? Three by 5. If you consider, it will be greater than 5, greater than, right? So how you are going to write that? As per that condition, there n is nothing but, for this integer part you have to add 1, so it will be 2. I mean, there the integer part is n is equal to q plus 1, integer part of this, so it will be 2. And what will be delta then? Q minus n, so nothing but 2 minus 3 by 5, sorry, 2 minus 8 by 5, what you have taken earlier, it will be 2 by 5, and then you will get q is equal to n plus delta. It must be minus 2 by 5. So there you are defining it as minus or plus. Then you will get the idea 8 by 5. So if you take fractions, it will become confusion for you. So it was defined like that. Okay. You just take the intention behind it. So you will take the definition as modulus there. So it will be minus or plus as per the case is considered. So here you need to take it as this is minus, this is plus. So this will be minus 2 by 5. So this will be minus 2 by 5. So you will get 8 by 5. So in this way it was defined. Okay. So once you perform totally gamma plus I delta, you will get the required thing. Please understand, gamma and delta may be something different. Please understand, gamma and delta may be under the rational part. You are taking the remainder as V into gamma plus I delta. Please understand this thing. Gamma and delta are basically in the fractional mode, maybe 2 by 5, 3 by 5, something else. So you are taking the remainder as V into this thing. So once you perform the multiplication, this will become an integer. That is the underlying thing here. So I agree to your word that gamma and delta basically looking like the fractional things. So the remainder, since you are multiplying with V, it will become integer after performing the thing. So you exclusively feeling that gamma plus I delta will be the remainder. It is not the remainder. V into this part will become the remainder. Clear now? Because initially, as per your thing, 0.8, 0.2, they will come gamma and delta. So once you multiply with this thing, then they will become into integers. So for your understanding, the best thing you can perform is you can take an example. Let me say, you can start with any two numbers and apply the data there. Say, suppose you have taken, say, u is equal to 2 plus 3i and v is equal to 4 plus 6i or something, or 7i. Now you perform the multiplication there. Is it possible to write u is equal to v into something plus something as per the notation what I have given? And easily you can understand that you will get the integers there by simply defining the thing what I have there given, m, delta, gamma, etc., etc. You can do by taking a small example on this. Clear? Because once you do with the numbers, then it will clarify your total doubts. Fine. So there the thing is, you are going to take the value as either positive or negative. Please understand, in order to get Q. If the value is less than or equal to this, it will be taken one way. If the value is taken more, then you can take the other thing. Please understand that. In order to get the value, I am not taking the modulus. Don't misunderstand me. I want to take the intention. Say you can write it as n minus q in that case. It will be very easy to write then. Obviously, you will get minus 2 by 5. Say. Our intention is just to write q is equal to some part based on the thing. You can take n minus q or q minus n. So without taking an example like this, you cannot do that. It's totally different. We have to take a problem and do. It takes a lot of time. That's why I'm giving the underlying idea behind it. In this way, the structure is defined. That's it. Fine. We will discuss deep into that once we finish with this result. Now, the question is, you got the remainder. If remainder is 0, it is okay. If remainder is not 0, then you have to verify the condition that d of r is less than d of v. So if you want to verify d of remainder is less than d of v or not, this thing we are going to do. So here, this is the part of remainder. V is nothing but c plus id. This is gamma plus I delta. So if you consider the d of remainder, as we know, whenever this type of notation is there, you can do the multiplication that it is nothing but c square plus d square into gamma square plus delta square. Because we have already verified, whenever you multiply two numbers of this form, this will be the output result. Then what happens? The maximum possibility for gamma and delta is you are exactly bifurcating the middle, because you are taking the values. If it is less than half, what to take? If it is more than half, what to take? So what happens here? If you take the possibility for gamma and delta is less than or equal to 1 by 4, because the possibility for gamma is at most 1 by 2. And similarly for delta it is 1 by 2 because you are taking the bifurcation in the construction at half. In the first half and second half you are taking. So whatever the fractional part you consider, you are doing at the middle. So gamma square and delta square you will get at most 1 by 4. So you can say that this value is less than or equal to c square plus delta d square into 1 by 4 plus 1 by 4. That is nothing but 1 by 2. So this is equal to c square plus d square into half. Since half is always less than full, this is less than c square plus d square. Therefore, d of remainder is less than d of v. Because c square plus d square is nothing but d of v. Hence, the remainder condition is also satisfied. Hence, it becomes a Euclidean ring. That is the whole idea. Okay? You just take a note of that. Any questions for anybody? Therefore, the ring of Gaussian integers is a Euclidean ring. That was the conclusion which follows. So if you are interested, let us discuss with the construction what is taken there. We can do that. Any doubts in proving this remainder condition? Please tell. Right? If you have any other queries, you can ask. Otherwise, we can conclude our session here. To the next class also, I will take some more problems based on these Euclidean ring concepts, and we will discuss other definitions also. I simply request you to take a problem like this. You take a problem and do the construction, hence you can easily verify what it is actually behind this construction. That gives the idea in a clear manner. Okay? Will you agree? Right. So apart from this, the total approach of the problem is clear for everyone. Accepted? What is meant by Euclidean ring and what is the approach for it? So if you understand the construction and how the function is defined, similar kind of problem is given in the previous three papers that Z of root 2 is an Euclidean ring. The same steps are exactly reproduced